This talk on quantum gravity is taken from a classical complex four-wave foundation of the cosmic quantum mechanism, the development of a model of fundamental rest mass quanta as simple harmonic oscillations of the spacetime continuum, driven by its expansion at resonant frequency and wave number. We will start with a discussion of kinematics and the geometrization of time, followed by a discussion of dynamics and the geometrization of mass, leading to the derivation of Newton's gravitational law in light of certain quantum principles, followed by some cosmological considerations and a statement with diagrams of the quantum metric as a modified chargeless extreme Kerr metric, and end with some general comments about the model and its implication for existing models. We start with some observations on kinematics and the geometrization of time. We can represent time as a compact dimension with this familiar form. For a given 3-vector r and 1 radian of motion, we have this scalar equivalence of space and time. From this, we construct a set of orthonormal bases. This can be shown graphically with r0 as a clock hand and t0 as the instant unit direction of time at an arbitrary spatial orientation from any point in 3 space. From this, we have the following related scalar terms. The same condition can be represented by rotating the entire circular clock face. In addition to the initial positive t, a negative time vector is shown here at the point of the arbitrary r, one of an infinite number of possible hands. The rotating clock circumference is orthogonal to r and to any arbitrary pair of coordinates in the plane of the clock face. The same instance in time is represented anywhere on that circumference. We can extrapolate this system to 3 dimensions as follows, where a second clock face, phi, rotates orthogonally to and with the same frequency as the first, theta. Note the position of clock face phi and t phi, coincident with t theta equals 0. T theta equals pi over 2. T theta equals pi. And at t theta equals 1.5 pi. Note that the clock face theta rotates constantly in the same direction with respect to a fixed position, while phi oscillates its direction of rotation as it spins in theta. Over one cycle of theta, an arbitrary r traces a figure 8 on a hemispherical surface, always towards the x3 poles on the leading side and toward the x1, x2 plane on the trailing side. It is clear that this representation of time is orthogonal to all 3 spatial dimensions. If we allow for continual minute contraction or expansion of r with the oscillation, t can be mapped to an indefinite 4th linear dimension. The same condition represented as the rotation of a dipole orthogonal to a fixed spin axial vector. Analysis shows that this arrangement is Lorentz covariant. Here T superalt is a time unit base in a moving reference frame and is contracted proportionally with the contraction in the space unit base R superalt, as determined by the Lorentz factor gamma. Thus, any time interval measured from that frame using T superalt will be enlarged or dilated with respect to that same interval measured using time unit base T. We can see this graphically in the following slide. Diagram A in the top box represents a Cartesian 2-dimensional spacetime as seen from fixed reference frame F sub alt. It is noted that this graphic representation is equivalent to the earlier mentioned statement using imaginary sense that I R sub alt equals T sub alt. R sub alt represents 1 unit of space and T sub alt 1 unit of time. The diagonal line C is the normalized speed of light in any reference frame, in which any contracted unit of space and time remain equal. The area above this line is the time-like area, and the area below the line is the space-like area of this depiction of space-time. The line V is the velocity of an object in reference frame M moving relative to F at 0.4 times the speed of light. The quarter circle r sub alt represents the polar coordinate limit of a space-time unit in F. In diagram B, the proper time tau sub alt is plotted on the F time axis as the time unit in F divided by the Lorentz factor gamma determined by V. As shown in detail in the bottom box, the corresponding gamma is found as the secant to the angle theta between the time axis and the contracted velocity v super alt. This line is found by orthogonal projection of the intersection of v and t sub alt at A. Back onto the quarter circle r sub alt at A super alt. In the Cartesian system of F, this corresponds with the proper or contracted unit time tau sub alt. A new polar spacetime for the moving frame M can be depicted by scribing a new quarter circle r sub alt. Back onto the r sub alt axis to give the proper or contracted unit length for M as seen in diagram C. The point B on line V represents time dilation as conventionally envisioned, as the amount of time that is viewed to have elapsed in F when viewed from M. The extension of V super alt to the line T sub alt at B super alt is the amount to which a unit of time has slowed down in M as viewed from F. In diagram C, a relativistic particle approaching the speed of light is seen to intersect the time T sub alt at space-time point A in F. This projection on the polar space-time unit of F at A super alt is projected onto the unit time coordinate for F to give the proper time and proper length for M. Thus, as A approaches r sub alt t sub alt in the Cartesian system for F, i.e. the speed of light, those same values in M tend towards 0 as seen from F, and time and length intervals in F as seen from M tend toward infinity. We find this arrangement in nature in the relationship of the Compton and de Broglie wavelengths. Next, we take a brief look at dynamics and the geometrization of mass. For a classical body or a quantum particle, mass is inversely related to the change in velocity under a given impulse. For a classical body shown here, the change is shown from a rest state, and r sub A is the displacement undergone during the interaction. For an impulse defined here, of force as shown, we can define the following inertial constant, tau, as a time-independent invariant of the interaction, which is true for quantum interactions. Giving the inverse relationship between mass and geometry, tau is thus the integral of the impulse with respect to time. It is related to the action S, which is the integral of that impulse over its displacement, using Maupertuis's principle. As both tau and the action, in this case h bar, are invariant, this means that the final spin velocity of the interaction is invariant and equal to twice the speed of light. We would interpret the doubling to indicate a reversal of rotation associated with a spin flip. In terms of the inertial constant, the spatial length represents the reduced Compton wavelength and hence the particle's angular wave number. The relationship of tau to h bar and the speed of light is shown and evaluated in the SI system. We should not be surprised to find it in a development of quantum gravity, though the development would be unchanged simply by using h bar over c. If we consider a rest mass quantum particle as a physical and not simply a statistical wave, the use of the inertial constant can facilitate understanding and obviate the frequent and repetitive use of h bar over c. Here are some properties related to that invariant. The linear inertial density of a wave-bearing medium, here interpreted as a 4D continuum. Substituting the wave number identity gives the following transverse wave-force relationship. Here we have the expressions for the rest mass and spin energy. The naught subscript indicates the fundamental or resonant frequency values. Our intent is to construct Newton's law from quantum principles while keeping with the principles of general relativity. Newton's law is stated here, with the final term showing the interpretation of the inverse square law as curvature. With the masses geometrized, this is dimensionally equivalent to force as the product of stress and inverse curvature, i.e. a curved area. In keeping with general relativity, T is a force stress and F is a tension force operating normal to A. Thus, F3 is a 3-tension stress proportional to some force stress. We would like to express this explicitly for an isotropic condition of F3. If we start with an equation of a tension stress from a 3-ball on a 2-sphere differential area, with the sum of the shear stresses in the 2-sphere, we have the condition shown on the left. For a force stress operating isotropically on a differential cube in a 3-sphere, we have the sum of the stresses at the vertices to give us the condition on the right. Returning to our proportionality, we can use this last geometric factor of gamma 3 with a unit area in this scalar stress equation. Assuming an invariant stress, we can differentiate as follows. Separating and inverting the functions gives us a differential for tension force with respect to stress. We will use this as the prototype for quantum gravity, where the force differential is the quantum gravitational differential and the area is the length unit squared. The other function gives us a differential for area, i.e. spatial scale, with respect to stress. We will find this related relationship is tied to the Planck area and thereby the Planck scale. We can express a quantum version of Newton's law as the product of the number of quantum particles of some fundamental quantum mass times a curvature expressed in a related fundamental quantum length times a quantum differential of force operating normal to the area of curvature. It is important that we recognize that a fundamental quantum mass does not mean the smallest measure of mass in a particle, but rather the mass associated with the quantum of smallest reduced Compton wavelength. Given these identities for classical mass and length in terms of quantum fundamentals, substituting into the quantum formulation gives us Newton's law, assuming the equivalence of Newton's constant and the terms in the brackets. Note also the equivalence of the gravitational differential and the stress term from the previous slide. Substituting the inertial constant over length for the mass, we get the equivalent for Newton's constant, shown here. With rearrangement, we can solve for the fundamental length, where the stress differential necessarily equals 1. Using the codata values for G, h bar over c, and the derived value of gamma sub 3, we arrive at the value shown, which is equal to the reduced Compton wavelength of the neutron. If we use the neutron Compton, the inertial constant, and gamma 3 in the right term of the first equation, we arrive at a value for G which is within the standard uncertainty. The neutron mass is shown next. This development does not say that quantum gravity is a neutron-only phenomena, but rather that it is the fundamental waveform. The proton is simply the neutron that has transmitted a small amount of its power and energy as the electron and neutrino, and stepped down its frequency accordingly, in response to a decrease in impedance of the vacuum that comes with cosmic expansion. Finally, the mass over length ratio developed above is shown as a linear inertial density with its relationship to the inertial constant. Some SI values are shown next for the gravitational quantum. For the fundamental isotropic tension stress, for the transverse wave force of the neutron, the gravitational differential divided by the stress is equal to the unit area differential, which evaluates to the Planck area. Rearrangement gives this covariant condition. Substituting our derived form for Newton's equation into the mass geometrization factor used in general relativity, making use of the classical wave relationship shown, shows it to be equal to the differential of the natural log of the expansion force stress divided by the linear inertial density. Thus, the natural log differential evaluates as shown here. The force stress of expansion is here. Most significantly, the stress natural log differential is equal to the ratio of the fundamental wave force differential and that force, of the gravitational quantum and that force, and therefore is equal to the ratio of the gravitational and the strong interaction, this latter being the operation of the wave force. We next have the following cosmological considerations arriving from the relationship between the neutron scale and the Planck scale. Here we have the square root of the differential area, which is equal to the Planck length. And the ratio of the neutron length scale to the differential is equal to the square root of the natural log differential and constitutes the current cosmic expansion factor, evaluated as shown. The product of the expansion factor and the natural log of 2 in terms of a doubling gives the following cosmic extent. Current estimates from observation are approximately 60% of that figure. Given a Hubble rate derived in a full development of this model, but consistent with observation, as shown here, if that rate is in fact the expression of an exponential expansion, the product of Hubble and the natural log of 2 gives a doubling rate as shown. The product of the Hubble and the expansion factor gives the number of doublings from an initial unitary condition, or the time in current units since the expansion began. The number for the age of the cosmos is consistent with the extent in terms of light years in the previous slide. With similar logic, if the CMB, according to the WMAP, is centered around 90 gigahertz, or a wavelength of 3.3 millimeters, and has expanded from an early epoch of beta decay, this represents a doubling of 30.34 times, or an age of 282.5 billion years, which is consistent with the first analysis. This observation indicates that R remains stable as spacetime and the CMB expands, and would indicate that such quanta did not have the geometry of the Planck scale at the primal epoch, which instead of emanating from a singularity, started expansion from a density as shown in the following slide. Thus, the Planck length is the ratio of the neutron reduced Compton to the cosmic extent, and a classical differential of the log of stress, and decreases with expansion. Alternately, while not contradictory, if we think of the cosmic extent as fixed, then what appears mathematically as expansion is in fact regional concentration of the extents. From this reference frame, R decreases over time, once again as does the Planck length. The energy per cosmic extent is invariant, reflected in a global differential, the natural log of the stress of 1. In neither case is the Planck scale a fundamental discrete scale. We would like to check ourselves and see how this relates to the macro world of general relativity, to see if we can anticipate the threshold size of a stellar black hole. Using the values above for inertial density and assuming a dense spherical packing of a neutron at the size of the reduced Compton gives the following parameters. The first equation gives the flat spacetime radius for a conventional mass, given maximum density, which is equated with a geometrized mass of the same amount according to general relativity. The solution should be the mass in conventional terms of a threshold stellar black hole. As we can see, this corresponds with the conventional wisdom of approximately 2 solar masses, no doubt arrived at by similar reasoning. Here we have a comparison of various extreme Kerr metrics along with the Kerr black hole threshold shown in the middle. Of interest is the fact that the universe appears to be within its own horizon, which conventionally would tend to imply that its constituents are contracting, and that there are black holes within black holes. Also, the mass in meters being equal to the reputed age of the universe times the speed of light seems a bit serendipitous unless, of course, that mass, i.e. the number of currently theorized nucleons, was estimated using the above geometrization equation. But this figure is not the currently theorized or observed extent of the universe, which is in the 150 billion light year range. What this appears to reflect is what the metric shows, that the proper time and scalar scales are covariant, as are the bookkeeper scales. Finally, it is noted that the hypothetical mass of the known universe at maximum density and a radius of 102 million kilometers would fit inside the Earth's orbit in flat spacetime. Here we have a chargeless extreme Kerr metric with the phi coordinate suppressed. In this analysis, we utilize a non-standard interpretation of the radial component. If the radial differential vanishes at the horizon, as does the divisor of the coefficient, instead of blowing up, they cancel, leaving dr as a zero vector, orthogonally rotated as a tangent vector, as indicated by the orthogonal sense in the last term. The result is that I equals IR, as shown, indicating a rotational speed equal to c. Thus, all motion is tangential at the horizon and at the speed of light. For a black hole, instead of a plunge to a singularity, all particles are bound to the horizon at a condition of maximum inertial and energy density. Next, we have the quantum time-like metric, which modifies the Kerr metric for the phi coordinates, where the complex exponent is defined as a counterclockwise rotation in the upper hemisphere and a clockwise rotation in the bottom hemisphere, both when viewed externally. Either real or imaginary could be used. The plus or minus curly brackets flips the sign of the phi rotation with respect to an arbitrary coordinate, theta equals 0. The same quantum represented as the cross-section of an extreme Kerr inertial sink. The following metric describes a mapping onto the static limit, the surface of the ergosphere. In the right-hand figure, the point at L equals 1 is the approach limit along the static limit toward the horizon. The path integral about SL at this point in each hemisphere forms 2 coordinate singularities. Here is a simplification for a fixed spin axis at the equatorial plane, where the cosine of beta equals 1, giving us the symmetrical time-like and space-like metrics, and indicates the orthogonal nature of the proper time and space differentials. These transformations can be represented by this antisymmetric orthonormal matrix of the 6 coordinate positions at the surface of a unit sphere shown by the rows, with their directional vectors with respect to those coordinates shown in the columns. In the presence of an external magnetic field, which includes that from any other interacting quantum, the magnetic moment of the quantum aligns with the field. The spin axis inclines toward a plane normal to that field and precesses. The 1/2 coefficient of isospin is apparent here and is developed elsewhere. Heisenberg uncertainty, then, is a result of the inverse curvature limit to the center of the oscillation and is not an independent parameter. We see in this animation of a half-spin particle that its oscillatory motion rotates the stress, but avoids the entanglement condition noted by mathematical spinners by oscillating the strain. Note that in this model, the oscillation is the three-dimensional representation of a four-wave or oscillation, and that it is driven by the expansion of the forecore. In summation, this is a formulation of quantum gravity as a function of spacetime expansion stress, where the inverse curvature is the quantum and the ergosphere is the domain of the strong interaction. It is part of an overall model of the quantum cosmic mechanism which includes physical quantization by way of a classical four-wave ontology. It accounts for the fundamental properties of quanta, including beta decay and charge, matter and antimatter, isospin, gravity, neutron, proton, and electron mass ratios and the missing mass of beta decay, and quark phenomenology. It has basic modifications of general relativity in which space-time mass replaces space-time. It admits torsion versus torsion-free. The primary time gauge is the expansion rate versus the speed of light.